This is John Black, Super Chemist. This is a new video series called New and Updated Time and Time Dilation. And this particular video is about how planets cause time dilation. You got three gravity machines, a rocket, a rotating thing, and a planet. At first, I thought that the rotating thing and the Earth were more similar than the Earth and the rocket, because a lot of things are inverse between these two things, the rotating thing and the planet. Look at the man. You're inverse, but you're exactly the same but opposite on where you stand. If this is rotating, the red man would stand here. His gravity would go down this way. The blue man would stand inverse on a planet, and the gravity would be inverse too. They're exactly opposite. And they're both circles. Come on, this looks very similar. Also, both of these have gravity, no matter what you're doing, unlike a rocket where you have to have your thrusters on. And then we realized that this formula for gamma, for time dilation, is the same exact formula for a rocket, for a rotating thing, and for Earth. They just changed velocity squared for tangent velocity squared and escape velocity squared. Escape velocity is linear velocity. Tangential velocity is the same exact thing as linear velocity, except you're going in a circle. If you're going 50 miles an hour down a road straight, and you're going down the road 50 miles an hour with your speedometer, going in a circle, you're still either way you're going 50 miles an hour. It's the same exact thing when it comes to time dilation. It's just one straight and one circular. Then look at this. So we learned that it's just stretching out this line. As you move, you stretch out this red line into a blue line, and it gets longer and longer the more you accelerate. When you go to constant speed, then it just you're stuck with that elongated second, and until you put your thrusters on to go one way or the other, it stays constant. Accelerate your velocity, you accelerate the time dilation. Constant speed, you have constant time dilation. And then if you look at these resultants here, the component vectors x and y through spatial dimensions, you can see, and remember these are not vectors of you going through space and time and you get the resultant vector. No, it's a photon going up and down vertically because he's in a photon clock, and also going horizontally because you are moving. And those are spatial component vectors, x and y, and it's for the photon, not you, and you get the resultant vector. Same way, look at this one. Take this part off and look at what you have. You have this right triangle with this circle thing here. And you have your same thing as up here, which is resultant. Look at the planet Earth. These are the geodesics that the north wants to go, south wants to go through. This is the straight line right here, this curved line. But the north and the south, they don't follow that inertial straight line geodesic path. So again, you get an x and y spatial component vector for your information carriers. And you can make another right triangle again, just like here, just like here. Notice how these two right triangles are inverse. This one has concave, this one has a convex. But look at the vertical and the horizontal. Doesn't matter. This concave or convex, it doesn't matter, because the resultant is from here to here, from here to here. This line, this hypotenuse, doesn't matter, because the hypotenuse we want is the hypotenuse that is a resultant, and that would be this. And you can do this triangle or this triangle, and you'll get the same result. Same thing, because the vertical and the horizontal are the same, either triangle you use. They're all the same. There's no difference. All three gravity machines work the same exact way, because they are all based on this. If you move through space, you make the space in between the plates on a photon clock, or you make the synapses, the space in between the neurons in your brain, bigger, or you make the space bigger between atoms in a hand on a mechanical clock. The information carriers are forced to move at sea, and now they have a longer distance they have to go. So this slows down, not time, but the flow rate of information for physics. So it has slowed down physics itself. And let's go over a couple things about gravity before we get into how this dilates time. Little g is the gravitational constant, like, we all know it, 9.8 meters per second square. It's the acceleration you get from ground level. Well, little g is constant, always. And by constant, I don't mean constant, it's 9.8 meters per second squared everywhere on Earth. No, I don't mean that kind of constant, okay? Because you have different densities of the Earth. More density means more gravity. You might be up on a mountain instead of on the surface, so you have less gravity here. So, yeah, it's not constant in that way. What I'm saying is every particular altitude, like ground, 1 meter, 10 meters, 1,000 meters, every point of altitude has the same exact little g. Like little g for ground is 9.8, say. It'll be 9.8 tomorrow. It'll be that a million years from now, 1,000 years from now. It's always 9.8. It's constant. Same way with 10 meters above the ground. This number right here represents that. 10 meters above this represents 1 meter. These three numbers, they are constant. They will never change. 1 meter over, not 1 meter above the surface around the whole Earth. It varies a little bit. But if you are right here, 1 meter above the Earth, then it will always be this number. Always. 10 meters, it will always be this number. And keep in mind, escape velocity values are proportional to little g values at each altitude, and they're constant. They whatever altitude you're at, that you have that same little g, which corresponds to the same velocity, escape velocity, and they're both constant at that altitude. Same up here. You have a different little g and a different escape velocity, but it is constant at this altitude. Because remember, this velocity squared is escape velocity squared. So here's the formulas for that, escape velocity. Notice that escape velocity matches up with the gravity. See, 2gr square root of. And 2 big G, m divided by r. It's gg. See these g's? On the surface of the Earth, it's 11,000, on average, it's 11,200 meters per second escape velocity. It will always be that escape velocity. Today, tomorrow, forever. Every altitude has a constant escape velocity. You can see at a meter. Look at the gravity, and keep in mind that it says 9.79 for ground because I live in the mountains. It's a little bit less, but anyways, you could see it goes out 1, 2, 3, 4, 5 places before it changes, and even that fifth place it goes from 2 to 176. That's almost 2. Come on. But it does go through you at 11,200 meters per second is the velocity, because that's escape velocity. So this is accelerating down. You don't really feel the acceleration as much, but you do feel the velocity when it comes to time dilation. If it's moving down at 11,200 meters per second, you have to, guess what, to escape that, you have to move 11,200 meters per second in the opposite direction. Gravity doesn't affect this ball. It doesn't affect anything except for space-time. It accelerates the space-time down. How do we know this? Gravity pulls down space-time and not balls or people. Because of these graphs they draw. Look at this graph. Here's a ball. It's falling. It stays in spatial coordinates F the entire time. And look at second 9. Where did spatial coordinates A, B, C, D, E, and F go? They're gone. They don't exist anymore. You can see the lines. They went straight into the Earth down to the center and disappeared, probably spit out in the middle of galaxies as dark energy or whatever you call it. See, if this was in outer space, this would be a checkerboard. And the ball would, it'd be 1 second, 2 seconds. You'd see a ball here, a ball here, a ball here. But it would stay within the line of the F coordinate. This is no difference. It just goes 1 second, 2 seconds, stays in the same coordinates. It never moves relative to space-time. This is why when you're falling in free fall, you're floating. And if you let go of a ball while you're in free fall, it floats with you. So yeah, it's a relative thing that you're accelerating to the ground, but relative to the space-time, you're just floating. You're keeping the same spatial coordinates. The space-time is being accelerated down by gravity. This is why a falling accelerometer says that it is inertial. And when you put an accelerometer on the ground, it says you're accelerating at 9.8 meters per second. Because you are relative to space-time. But the space-time is the one that's actually accelerating through you. But that comes to the equivalence principle. That's why it's equivalent, because you can go through space-time using velocity and acceleration, or you can use, or the space-time can accelerate or go, have great velocity going through you. Either way, it's the same thing. Your photons and your information carriers, they are attached to this grid. When I say information carriers or photons are attached to space-time, I just mean that relative to space-time, they will always be moving at c. You cannot stop that. The grid that you drive through with your rocket, or this, it is attached to that. And if your photon clock is going like this, right, and you have space-time going this way, that means instead of having to go up to here, you have to keep moving this way at 11,200 meters per second, just like space-time is going here. You have the escape velocity here, and you have your regular up and down. That's two spatial component vectors, x and y. So what is my whole point? My whole point is basically this is the same exact thing as a spaceship. The acceleration doesn't really come into play except for your physics. The only thing that time dilates is velocity. Your escape velocity works exactly the same way as your regular velocity in a rocket. There's only one different thing is you put your rocket on and you go from standing still, and your line grows bigger and bigger as you accelerate. The line representing your second. It gets stretched out the more you have your thrusters on. But as soon as you stop your thrusters, as you can see up here, the line stays constant. So your time dilation stays constant. What's the difference on Earth? There is no standing still. It's all constantly, every second, today, tomorrow, and ever, forever. It's going to be 11,200 meters per second velocity. It doesn't change. There is none of this. It just is constant. And that's the only difference between a planet and a rocket. If see this little bit of acceleration here, because say you're 10 meters tall, well, you would have some little bit of acceleration, but it's so tiny, all right? And we know this is not the acceleration is not causing any time dilation. Why? Because on Earth we would be time dilated into infinity. Acceleration on Earth does not change the velocity. Remember that. Escape velocity is always the same on the surface of Earth. So even though you're accelerating through a little bit, it doesn't change your velocity. When you're in a spaceship, your acceleration always, 100% of the time, will change your line length of your second. It will elongate it because you are changing your velocity. Here you're not changing the escape velocity, so you're not changing your velocity. This acceleration changes your velocity, changes your line length. This does not. Therefore, this acceleration on Earth does not have anything to do with time dilation. On Earth, it always has the same length of a second. If you turn off the rocket engines and you just go constant velocity and you go 11,200 meters per second, you get the same exact time dilation as you get here. You get different physics, but you get the same time dilation. Now, if you accelerate at 9.8 meters per second squared like the Earth, sure, you'll have the same physics, but now you will time dilate different because the accelerated rocket will keep getting his line more and more bigger. It will time dilate more and more and more. You accelerate your speed, you accelerate your time dilation. Here, it doesn't happen. All three of them are exactly the same thing. A rotating thing, the rocket, and the Earth. Why? Because all three of them are gravity machines, and that's how gravity machines work. They all work the same way. Because instead of going up and down in the vertical, in the y-axis direction, like you'd normally do in a photon clock, now the information carrier must also move in the x-axis, right? Because you are moving, and so it needs to move in the x direction just to keep up with you. So these are both photon spatial component vectors, and now has a new resultant vector. You can make the same triangle here. Your photon clock would be going here. Space-time velocity is going that way. You make a little triangle, just like up here, just like down here. It's the same exact thing. Your two component vectors are your x and y spatial vectors, and we're talking about a photon, not you, when we do these resultant vectors. That's why I always say time is a result, because it's a resultant. It's a result of information carriers and photons having and forced to be moving at a constant velocity. So if you make this line bigger and they have to go at a constant velocity, you slow down not time, because time is a mathematical construct. It's an idea. It's an abstract noun. What you slow down is the flow rate of information. This information flow rate is for physics to happen. So you are slowing down physics, the rate at which physics can flow.